Hello, my people. Hope we're doing well. This is the solution manual video, whatever you want to call it. Me working through quiz number 5. Let's call it that. Again, we start with we have a section where I asked you to verify 3 of the 4. And the reason why I did that is just because, it winds up just being, sometimes you have synapses misfire and you just can't see it, okay? And that's fine, and that's why, 3 out of 4 I thought was fair. Let's go ahead and start with the first one. We notice that the left side is tangent, okay? Now we have in the numerator cosine 2x. Now, we obviously are going to need to change the form of that. The question is which form. Ultimately, you need to decide on the 1 minus 2 sine squared x. And the reason is we eventually need to get it to a monomial. Because, if we have a monomial in the denominator and a binomial in the numerator, we can separate the fraction and it still winds up being a binomial. The way that we basically simplify and get a monomial is if we can transform the numerator into a monomial. And of course, when you do it this way, this positive 1 out here will cancel with this negative 1. Now, sine 2x doesn't really have any options, okay? Now, when I distribute this, I'm going to get 2 sine squared x over 2 sine x cosine x. The 2's cancel. One of these signs cancels with that sign, and you're simply left with sine over cosine, or, oh my gosh, tangent. Yay! Okay. Now, that one should have been straightforward enough. Let's go ahead and look at the next one. The next one winds up being a little bit, some people just kind of didn't like this one. And the reason is that we weren't given an identity for a sum and difference for secant. But you were given one for cosine, and all this is right here is 1 over cosine x plus y. And you also need to go ahead and look over here on this one and say to yourself, I recognize the fact that that has both secant and tangent in it, and both secant and tangent have something in common, and that is a denominator of cosine. And so this implies a complex fraction that has denominators of cosine x and cosine y. Okay, well, how do you get rid of denominators of cosine x and cosine y? Well, you multiply by cosine x and cosine y. Now, what that does to the numerator is real simple. It's just secant x times cosine x, well, they're reciprocals of each other, that equals 1. Secant x and cosine x, well, they're reciprocals of each other, so that equals 1. When I take that cosine x, cosine y, and distribute it to both terms in the denominator, this first term becomes cosine x, cosine y, and when I distribute to the second term, the cosine x combines with the tangent x, canceling with its implied denominator, and simply leaving sine x. This cosine x does the same thing, this cosine y does the same thing with tangent y, because basically it's cosine y times sine y over cosine y. The cosine y's cancel, leaving sine y. Now, this in the denominator is a recognizable sum and difference identity. It is cosine x plus y, which of course, since it's in the denominator, can be rewritten as secant x plus y, and that is exactly what we had on the left side. Hurrah! Hurrah. Okay. Now, let's go ahead and take a look at the next page. Now, some of you did this the longer way, and that's fine. You're going to kick yourself when you see the short way. So the long way, I'm going to go ahead and do it on a separate sheet of paper. I did it in enough space when I was using a pencil, but I'm using a pen so you can see what I'm doing here. So if I have tangent x plus y minus tangent y over 1 plus tangent x plus y, tangent y, I need to figure out how to make that tangent x. All right. Now I can use the sum formula for both of those tangent x plus y, and I'm going to get tangent x plus tangent y over 1 minus tangent x tangent y minus tangent y, all of that over 1 plus, okay, we'll go ahead and put this in parentheses, tangent x plus tangent y, 1 minus tangent x tangent y times tangent y. Now that is a mess, and I hope nobody is going to argue with me about that. But it is a complex fraction, and so predictably I'm going to multiply through by this denominator, both the big numerator and the big denominator, in order to get rid of it. So let's go ahead, and that's 1 minus tangent x tangent y, 1 minus tangent x tangent y, and at this point it is getting awfully messy, and you're thinking, why in the world would I ever do this? And of course I'm agreeing with you. Now when you distribute it, basically you need to take this and distribute it to this first term, which by first term I mean that whole fraction, and then to the second term. When you multiply it by this first term, it cancels with the denominator and leaves you tangent x plus tangent y. When you multiply it by this second one, remember it's negative tangent and it needs to be distributed across here, and you're going to get negative tangent y plus tangent x tangent squared y. Okay, well, let's go ahead and do it with the denominator. Again, we're going to have to distribute to both terms, this whole thing being the second term. When I distribute to the first term, it's multiplied by 1. It just becomes 1 minus tangent x tangent y. And when I multiply by the second term, it cancels with the denominator and simply leaves you tangent x tangent y plus tangent squared y. Now, you should be recognizing the fact that there is cancellation going on in both the numerator and denominator. This is positive tangent y. This is negative tangent y. This is positive tangent x tangent y. This is negative tangent x tangent y. And what I have left here is tangent x plus, let's go ahead and factor out 1 plus tangent squared y. And then in the denominator, I simply have, oh my gosh, will you look at that, 1 plus tangent squared y. Boom, boom. I just have tangent x. Now, that is doable. There is nothing in that problem that you do not have the skill set to perform. The problem is that it's big, it's messy, there's a lot going on, okay? Now, the easy way to do this is, remember that when we're talking about the sum and difference, you know that tangent of u minus v is equal to tangent of u minus tangent of v over 1 plus tangent u tangent v, right? We know this. But what gets into your what you fail to actually recognize sometimes, because anytime notation is larger than just a variable by itself, it distracts us. X plus y can be my u. It's a binomial, but it's still one quantity, right? And, you know, basically what I'm saying is that if u is equal to x plus y and v is equal to y, then this totally becomes tangent of u minus V. And of course, that angle measurement expression simplifies to x. Ta-da! Yeah. And that's, really, really frustrating. I get it. But I mean, it illuminates a larger point that I've mentioned before, which is the first step to not getting distracted by large notation is to recognize the fact that it's possible to have a very simple problem that looks really complex, and the reason why we can't see it is we're letting the large notation distract us. X plus y is a binomial, but it can be treated as one quantity, and especially when it's in parentheses together in an angle measurement expression. All right, let's go ahead and look down here. I recognize that I have sine of 3x. Well, I know I have sine of 2x, but I don't have sine of 3x, so what I need to do is turn this into sine of 2x plus x. And then I can use the sum formula for sine. And I get sine of 2x cosine x plus sine of x cosine of 2x. And again, of course, the problem is the fact that you have cosine here, and cosine of 2x has 3 different versions. But do you see any cosines over here? I don't. So that tells me exactly which version of the double angle identity for cosine I'm going to use. Now sine of 2x becomes 2 sine x cosine x. And I've just specified which of the cosine 2x double angle identities I'm going to use. And now I simply need to distribute and see how I can sort of collect terms and all that sort of jazz. Let's go ahead. That becomes 2 sine x cosine squared x plus sine x minus 2 sine squared x. Or sine cubed x, sorry. That's my bad. Now, what we need to do is we need to recognize, first of all, that this right here tells us that we're probably going to factor out a GCF at some point. I see that GCF in those 3 terms. Let's go ahead and factor it out. And I pull out this sine x, but hey, I tell you what, while I'm at it, I see this cosine squared. Ain't no cosines over here. So I know that that needs to be changed into 1 minus sine squared. When I pull a sine out of that second term, I'm simply left with 1. And when I pull it out of this third term, one of them goes away, but 2 of them remain behind. And basically, if you just, distribute this 2 and then collect like terms, what winds up happening is, of course, you wind up getting exactly what you have over here on this other side, and we have indeed verified. Yay! Okay, now that we're done with the verification problems, I'm hoping that that was clear and that you understood all of that. Let's go ahead and move on to the solving. Now, I warned you again and again and again that I was going to give you different intervals, okay? Intervals, 0 to 2 pi. Now, the first thing that you need to remember is not only am I looking for a finite number of solutions, I'm looking for all of the solutions. So sometimes people gave me the plus pi n or plus 2 pi n or whatever. Not what I asked for. That's a negative infinity to infinity. Sometimes people gave me one solution but failed to give me the other solution that is within 0 to 2 pi. Okay? Not a full answer. Some people, some people basically, they gave me, some people gave me the negative infinity to infinity. Some people gave me negative answers. Well, here's the thing. Especially when you use your calculator, you sometimes can get negative answers, like when you're using arcsine in your calculator. but are negative answers included in this interval? The answer is no, they're not. Okay. Now, this is a quadratic, but it has two different trig functions, so I'm going to need to change this cosine to 1 minus sine squared. And while we're at it, why don't we go ahead and bring that 3 over to the left-hand side, because we're looking for a quadratic that we can factor, or at least use, completing the square or Pythagorean theorem, quadratic formula or whatever on it, okay? So what we're going to do is basically we need to distribute that 2, and then we need to recombine everything. So 2 minus 2 sine squared plus 3 sine minus 3. And here's the thing, that's going to give me a negative leading coefficient. I don't like that, so let's go ahead and at the same time multiply through by a -1. Now when I collect like terms, and the only ones I need to collect are the constant, I get that. Now that does factor, okay? It factors into 2 sine x minus 1 and sine x minus 1. Okay, well this is going to ask me when is sine equal to 1/2, and this is going to ask me when is sine equal to 1. Well, remember, sine is equal to 1/2 twice on the unit circle, twice in one revolution around. It happens to be at pi over 6, but also at 5 pi over 6. Now sine is equal to 1 only once. That is at pi over 2, and yay, there we go. Now, this next one was a little more difficult. It was 4 sine x cosine x, and you're thinking to yourself, oh, if only it were 2 sine x cosine x. Well, it is, or at least it can be. So, you can either basically split the 4 apart into 2 times 2, or you can just do a little bit of the work that you're going to do anyway ahead of time and just divide both sides by 2. There's no hard and fast rule that says you have to either leave the 4 there or divide by the whole thing. You can certainly divide by half of it. And when it comes to this, this now becomes sine 2x by double angle identity. Now, here we're going to be dealing with only from 0 to 2 pi. Now I've showed you the way that I like to do this to ensure that I get all of the solutions, but you don't have to do it that way. The way that I do it is if I know that there is a change in period, I treat it like a negative infinity to infinity and then use that answer to figure out what exactly happens between 0 and 2 pi. Now, sine 2x, sine is root 3 over 2 when the angle measurement is pi over 3, and when the angle measurement is 2 pi over 3. Okay, but that's plus 2 pi n. That happens over and over and over every single time. Now, it's tempting just to divide through by 2 and give me pi over 6 and pi over 3. But as this indicates, since there is a change in period, what happens is not only will pi over 6 satisfy this, but 7 pi over 6 will as well. Pi over 3 will satisfy this, but so will 4 pi over 3. And that's why I kind of go through and treat it, when there's a change in period, I treat it as if it's not 0 to 2 pi, so that I can look at these and go, okay, pi over 6 plus pi n if it were negative infinity to infinity, but which of those occurs between 0 and 2 pi? And the answer is pi over 6 and 7 pi over 6. And the answer over here is pi over 3 and 4 pi over 3. Those are your 4 answers. Alrighty. Let's go ahead and find the solutions on the interval negative infinity to infinity. Okay? Let's go ahead, and here's the thing. We look and we see cotangent and we go, oh no! But here's the thing, cotangent is just the reciprocal of tangent, okay? So if you know your tangent values, which you should, you say, okay, well that's cotangent squared x is equal to 1/3, which, and you can go ahead and just turn it into tangent at this point. That's tangent squared is equal to 3. So you're looking for the places where tangent x is equal to positive or minus √3 from negative infinity to infinity. Well, remember, okay, that tangent has a period of pi, not 2 pi. It has a period of pi. And therefore, what we need to be doing here is we need to be accommodating that. Now, I know that, and if you're not good on the tangent values, remember that tangent is sine over cosine. So you can sort of unsimplify √3 and say, well, tangent x is equal to √3, but that's the same thing as √3 over 2 over 1/2, and we know that tangent is sine over, if I can actually write cosine, sine over cosine. And basically you're looking for plus or minus. So where is sine √3 over 2 and cosine 1/2, and just put out of, like, absolute value, just put out of your mind the pluses or minuses? Well, sine is √3 over 2 and cosine is 1/2 at pi over 3. Okay, so one of those answers is pi over 3, and of course since tangent has a period of pi, it's plus pi n. But when we're thinking about sine and cosine having that √3 over 2 and 1/2, you also got to think of the places where they have those magnitudes, but they have opposite signs. And that would, of course, be second and fourth quadrant. And so in the second quadrant, it's going to have the same reference angle, right? So it's still going to be an over 3 answer, but it's 2 pi over 3 plus pi n. And there you go. Now, of course, that's actually confirmed when you use your calculator, and you can use your calculator to check that answer, but that's kind of what's going on there. On this next one, you have basically an implied quadratic, but you need to basically change the form of cosine 2x, and since this is already cosine, that tells us which one of those cosine identities I'm going to use. And you thought, oh my gosh, it was going to be quadratic. What if it doesn't factor? You want to know what? It doesn't matter, because at this point, the constant terms go away, and all I'm left with is a GCF problem. It's asking me where is cosine equal to 0 and where is cosine equal to negative 1/2. Well, cosine is equal to 0 at pi over 2. But it's also equal to 0 at 3 pi over 2. And remember, this is that unique situation where they just happen to be on opposite sides of the unit circle, and therefore instead of pi over 2 plus 2 pi n and 3 pi over 2 plus 2 pi n, you can actually just shorthand that as pi over 2 plus pi n. Now, whereas cosine equal to negative 1/2, well, we've already been talking about where sine is √3 over 2 and cosine is 1/2. It's where the reference angle is pi over 3, but I'm looking at the negative values, so of course it's going to be in the second and third quadrant, right? Left from the y-axis. And so we have x is equal to 2 pi over 3 plus 2 pi n, and 4 pi over 3 plus 2 pi n. Alrighty? Okie dokie. Last page of, regular credit problems. If sine x is equal to √2 over 2 has two solutions on the interval, and of course it does, pi over 4 and 3 pi over 4, then how many does sine of 2x have? Well, remember that, and just think about it graphically. If, here, let me get a ruler out. If you think about it graphically, okay, and we'll if this is sine of x, okay, And if this is 1, then root 2 over 2 is 0.7, right? And so it's these two values, pi over 4 and 3 pi over 4. You need to remember that sine of 2x, if you think about y is equal to sine of 2x, that's a horizontal shrink, right? It doubles the period. So it halves the period and it doubles the number of times it oscillates in the given interval. Okay, well, then you have this point, this point, this point, and this point if you keep extending the line out, right? Okay, well, that means that it has 4 solutions. It's not pi over 4 and 3 pi over 4. It's pi over 4. It's pi over 4 divided by 2, okay, which is pi over 8. So it's pi over 8 and 9 pi over 8. That would be these two. And 3 pi over 8 and 11 pi over 8, these two. And what I was looking for is I was looking for two things. How many does sine 2x is equal to root 2 over 2 have? It has 4 solutions. And then I was looking for a legitimate explanation, and the easiest way to do that, what I was actually looking for, since this is the way I described it, is basically a change in period, okay? Or just call it a horizontal shrink. It brings twice as many oscillations into the same interval, okay? Now, let's go ahead down here. Now, using known identities to determine the exact value of sine 11 pi over 12. Now, we did this. Now, we didn't do a huge number of them, but the whole point of this is to emphasize the fact that these are not only true for when there's variables involved, but they're also true when numbers are involved, which should make sense because variables are just numbers. They're just not known to us. And this is the same principle that, you know, if I have 165 and you go, okay, well, what are its factors? Well, you could divide by 5, or you could recognize the fact that that's 169 minus 4, which, by the way, is the difference of two squares, right? And so that's 15 times 11. It works for numbers too, right? I mean, I know that we use it we usually only use it when we're thinking about variable expressions, but you know, the difference of two squares works for variables because it works for numbers, right? And you know, so I mean, and so basically this principle holds. So I mean, you could actually do it for, you know, 168. Okay, well, how is that? Well, this would be easy. This would be a little bit more difficult because that's 169 minus 1, so that's 13 plus 1. And 13 minus 1. We're going to be doing the same sort of thing. It's the same kind of logic here. Now, the great thing about 11 pi over 12 is that there's no one way to represent that with unit circle values. There's plenty of ways. Okay, 11 pi over 12, that can be 3 pi over 12 plus 8 pi over 12, both of which reduce. That's pi over 4, and that's 2 pi over 3. Those are both unit circle values. So, I mean, you could do sine of pi over 4 plus 2 pi over 3. But 11 pi over 4 is also 15 pi over 4 minus 4 pi. I mean, 15 pi minus 4 pi. Or, you know, both of which have common factors with 12 and will reduce. It can be, I don't know, I mean, it can be, instead of 3 and 8, it can be 6 and, no, 6 and 5 won't work. 9 and 2 will work, sure. You know, 11 pi over 12, and that becomes 2 pi over 12 plus 9 pi over 12. This becomes pi over 6, and this becomes 3 pi over 4. Those are both unit circle values. Okay, so let's use this first one right here. I know that sine of 11 pi over 12 is sine of pi over 4 plus 2 pi over 3, which is going to be sine pi over 4 cosine 2 pi over 3, plus sine 2 pi over 3 cosine of pi over 4. And then you simply evaluate those, because you should know these values. Now this is root 2 over 2, and so is this, right? You simply need to decide what the value of these are. Well, when the reference angle is pi over 3, cosine is 1/2. But this is in the second quadrant, so that's negative 1/2, okay? And this, of course, is root 3 over 2. I'm going to change the order so that the second term is negative, so it's a reasonable difference. That's root 6 minus root 2 over 2. That is an exact value. And we used the sum formula for sine in order to figure that out. And, you know, like I said, you could have used the difference formula. It could have been sine of 15 pi over 12 minus 4 pi over 12. And that winds up being sine of, and that's what, 5 pi over 4 minus pi over 3. And the values still would have worked out to that, okay? Now I'm going to go ahead and do the extra credit problem real quick. You simply needed on this one to recognize, and again it's one of those did you let it distract you sort of moments. You need to recognize that x is a double angle if you think of it as 2 times x over 2. So on this left-hand side, we can do 2 sine x cosine x over 2 sine x. Those cancel. I'm left with cosine x. And then what you need to do from here is you need to say, well, that's cosine of 2 times that angle measurement, which can then be changed into cosine squared x over 2 minus sine squared x over 2, and that of course is identical. And you could work on the right hand side as well. You would just be reversing this same logic, right? You would have gone from this difference to this to this. The only problem is you would have to actually recognize that you needed to multiply cosine by 2 sine x over 2 sine x. And that would have been the only difficulty. So it's actually a little bit easier to start with this left-hand side. But that right there is the verification. Okay. I hope that this has helped you understand those things that you got wrong, if you did indeed get a substantial amount of stuff wrong on quiz number 5. I'm going to go ahead and do quiz number 6 here before long. And as with the last one, I will be scanning both the answer key as well as this document that I've used to actually demonstrate all of this stuff. So if you have any questions, please do shoot me an email. Bye.